One emoji has crashed million-dollar systems. It has corrupted databases, broken APIs, and turned perfectly normal text into gibberish like café. The crazy part? Most developers still don't fully understand why. Let's fix that in the next few minutes. You've seen this before. You type café, it shows up as café, or someone types an emoji into a form and the entire database throws an error. It's not magic. It's not a bug in your code. It's character encoding, the invisible foundation of every text interaction in the digital world. And once you understand it, you'll never look at broken text the same way again. Computers only speak numbers. When you type A, your computer stores the number 65. When you type A with that little accent, it stores... Wait, what number is that? And who decides? This is where things get messy. Back in the 1960s, Americans created ASCII, a simple system with just 128 slots. A became 65, B became 66. Clean, simple, English only. Want café with the accented A? Too bad. Want Chinese, Arabic, or an emoji? Impossible. The rest of the world was completely locked out. Computers only knew English, and the world wanted more languages. Enter Unicode, humanity's answer to the character crisis. But here's where most people get confused. Unicode is not an encoding. Read that again. Unicode is not an encoding. Think of Unicode like issuing every character on Earth a passport number. It doesn't matter where the character is from or what language it belongs to. Everyone gets a unique ID. A is passport number 65. E is passport number 233. The Chinese character zhong is passport number 20013. The grinning emoji is passport number 128512. So Unicode tells you what each character is. It doesn't tell you how to store it. Unicode fixed identification, but storage was still broken. That's where UTF-8 comes in, the brilliant shipping method for Unicode's catalog. UTF-8 is variable width. Think of it like an accordion that expands only when it needs to. English A takes 1 byte, exactly the same as ASCII. French A takes 2 bytes. Chinese zhong takes 3 bytes. An emoji takes 4 bytes. Same catalog, different storage sizes. Let's get concrete. The word hello takes 5 bytes. The Chinese ni hao takes 6 bytes for just 2 characters. A single emoji takes 4 bytes. Same characters on screen, wildly different storage costs. This is why international websites need 2 to 3 times more database space than English-only ones for the same content. And here's the mystery worth pausing on. If Unicode already gives every character a number, why do we even need UTF-8? Because Unicode only assigns the number. UTF-8 decides how to actually write that number into computer memory in a way that saves space when it can and expands when it must. When you see café instead of café, it means someone tried to read UTF-8 text using the wrong encoding. It's like trying to read a French menu with an English-only dictionary. The bytes are technically there. Your tools just can't interpret them correctly. And here's a myth worth busting. UTF-8 does not mean 8-bit encoding. The 8 refers to the minimum unit being 8 bits. UTF-8 can actually use up to 32 bits, 4 bytes per character. It's 8-bit based, not 8-bit limited. Believe it or not, every ASCII file created back in the 1970s is still valid UTF-8 today. And it's like designing a brand new phone that can still call rotary phones from the 1950s. That backwards compatibility is a huge part of why UTF-8 won. And UTF-8 didn't just win. It dominated. Over 98% of all websites use it. UTF-8 gives English text the same tiny file sizes as ASCII, while still supporting every language and every emoji on Earth. That combination made it the perfect choice for the internet. This isn't just theory. Encoding bugs cause real damage every day. Corrupted databases when users enter emojis the system can't handle. Broken websites displaying café instead of café. Failed file imports between systems that both technically support Unicode but disagree on how to interpret it. Those maddening special character not allowed errors that seem to come from nowhere. Here's the complete flow. You type E, Unicode says that's character 233. UTF-8 says I'll store 233 using 2 bytes. The computer saves those bytes. Later, UTF-8 reads them back and tells Unicode this is 233. Unicode says that's E. You see E on your screen. Every link in that chain has to work correctly, or you get café. So now you know the secret. Unicode is the what, the master list assigning every character its passport number. UTF-8 is the how, the smart variable width storage method. ASCII is the grandfather still living inside UTF-8, kept alive by that elegant backwards compatibility. So the next time someone sends an emoji that crashes a database, or you see mysterious text like café, you'll know it wasn't magic. It was simply Unicode, UTF-8, and the mismatch in how those bytes were interpreted. Please like and share if you found this useful, subscribe for more, and I'll see you in the next one.